back. In this video, we're going to discuss the algebra of propositions. So we've already done a few lectures at this point on propositions, and we built up compound statements from atoms. These were the things that I said were either true or false, and we could not break them down any further. So what do I mean by algebra? Well, we've already hinted at it to some degree. We just didn't necessarily use that language yet. Okay, so what do I mean? Well, if you think back, you'll remember that I said P implies Q. This is logically equivalent to not P or Q, right? So the idea is that there is an equivalence between them. So in some sense, this is an algebraic relationship because this symbol, this arrow, I can convert it to this and this, right? And then I can do some stuff on that, right? In the last video, I said it is not the case that A or B is different than it is not the case that A or B, right? In other words, and I think it was and, not or. So I said that this is different than this, right? And so how can we make sense of that? Well, it would be nice to know how negation acts on this term. How does it push through, right? And for that, we need an algebra. Okay, so a quick comment before we get really deep into the algebra. The Algebra of Propositions, this is the title of chapter 2 of the book, and it begins on page 10. And you should be reading your book. You know, if you have it, you should be reading it. If you don't, follow along the best you can. But for those that are, I would encourage you try to read every single line. Go slowly, go through. Okay. So that first paragraph, those first 2 or 3 paragraphs, all the way down to Theorem 2.2, Principle of Substitution, that stuff looks maybe a little scary. So I'm going to go through that really quick. And when we're finished with this, then we'll get into laws of the algebra of propositions. Okay, so the first couple of words, it says some propositions P, so some propositions P, and then it has this parentheses, and it has little p, q, dot, 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 right? And then it says contain only t in the last column of their truth tables, and then a lot more stuff, right? And I think for a lot of new people, they look at this and they immediately say, well, what the heck is this, right? What the heck is this? Okay, so this is, the book doesn't do a very good job explaining what that means. So I'm gonna briefly explain it. So you might, think back to functions, right? So you have a function f of x, right? And how do we describe f of x? Well, maybe f of x is x plus 4, right? So it's a function, right? What is this function? Well, we use f, I suppose, because f and function starts with f, but you can use other letters, h or g, k, any symbol will do. And when you write this parentheses, you're saying that this has an argument, right? And that input is x, and the output is x plus 4, right? When you get into higher mathematics, sometimes you, or I should say often, you have more than one variable. So you might have x and y, right? And we could take 2 times x squared and then add, say, 3y. And if x, let's say we wanted to evaluate this, right? So this would mean I plug in 1 for x, I plug in 4 for y, and I would get 2 times 1 squared plus 3 times 4, and that's going to be 12 plus 2, so that's 14. Okay, so why am I telling you all this? Well, just like this function g is a function of x and y, propositions, right? Propositions are made up of atomic propositions, right? Atomic propositions. So, right, so you have, here's the full proposition, right? The full proposition. And then you have these atoms, right? By the way, this language I've been using so far in this course, it has a history that goes to Wittgenstein, Ludwig Wittgenstein, and he's one of the famous philosophers, logicians, who uses this language of atoms. So I think we largely are borrowing that language from him. So his PhD advisor was Bertrand Russell. He was also a very famous philosopher and mathematician. Okay, so if I write something like, let's say, PQ, just like in the case of a function, right? The way I define P, the proposition P, is just how I use these letters P and Q. So for example, I could do something like P and P, or not Q, right? And that's perfectly reasonable. So you haven't seen anything like this where you use the same letter twice, but it's perfectly fine. And of course, because these two P's appear twice, if one of them's true, the other's true. If one of them's false, the other's false. So, just intuitively, we know that we get P, the P and P just reduces to P, and you get P or not Q, right? So if that doesn't help, maybe put some parentheses around it. You see that it got reduced, and now I'm going to remove those parentheses. Okay, so hopefully that was clear. That's all that sentence was saying. Now that that's out of the way, you often hear philosophers talk about tautologies. So think back to your truth tables. So it could be the case that in the final column, every row is just true, right? So for example, I just made the claim that P and P is logically equivalent to P, right? So P and P is logically equivalent to P. Well, if it's true, well, actually, we'll have to come back to that because we haven't figured out how to use this symbol yet. You've only been using that sort of at the meta level, not the object level. So let's we'll come back to that. Okay, so if the final column is all true, we say that the entire proposition is a tautology, and if the final column is all false, we say it is a contradiction. Okay, so if the final column is all true, then the negation of it will be all false. So that would mean that every tautology has a negation, which is a contradiction. Every contradiction has a negation that is a tautology. So there's a correspondence there. Okay, so the first example we can think of is P or not P. So this is often called the bivalence principle. It says that at least one of these things has to be true. Now, I misspoke. This is the law of excluded middle, which says that this statement is true. We're not going to get too deep into that philosophy of logic. It gets rather complicated. But let's see that this is a tautology. Okay, so you have P, you have not P, and then you have P or not P. Right? So P is either going to be true or false, and those are, it's the only variable, right? So 2 to the 1 is 2, so that's why there's 2 rows. And if P is true, this is false, and if this is false, this is true. And hey, look, this final thing is always true because, well, at least one of them is always true. So the point here is that this is a tautology. So I'm going to make a quick side note. So in mathematics, there are these people known as the constructivist. So in mathematics, we have constructivists. And they reject this law. Okay, so what do I mean? So they simply don't allow this statement to be true, right? Though it is true under classical logic, right? So what we're doing in this class is called classical logic, right? And so the constructivist says, I need a proof, right? So there's this thing called a proof by contradiction. And we're going to come back to this when we get into syntax. But basically the idea is that if you can prove that not P, this is going to lead to a contradiction after you do some proof, then the classical mathematician is going to say, okay, so not P leads to contradiction, then I can conclude P. But the constructivist is going to say, I need an explicit demonstration that P is true. You cannot merely show me that not P is false, right? And so their line of reasoning is that as soon as you have this statement here, P or not P is true, together with the fact that not P is false, there's going to be an inference we're going to learn later that will, in our syntactic toolkit, it's going to say that if you had those two things, then you could conclude P, right? So they don't have any problem assigning a false value to not P, but it's making that inference to P from this right here. Okay, so if that is a little confusing, don't worry about it too much. So now I'd like to get into some algebra. But before we do, we're going to motivate this with an example that I mentioned in the last video. So you have P and, sorry, not P and Q, and you also have not P or not Q. And I claim that these two are actually equivalent. So let's think about why that would make sense. Suppose P was 2 plus 2 equals 4. And actually, let's make it something that's not necessarily true. Let's make it something contingently true. How about there's a cat on my porch and it is raining, right? So let's let P be there is a cat on my porch and Q is it is raining. Okay, so very, very clearly, not P is going to be there is not a cat on my porch, right? So previously I said we might prefer to say it is not the case that there is a cat on my porch, but that's a little tedious to say, and just by understanding how basic English works, we know that we can just say there's no cat on my porch. It's the same thing saying it is not the case that there's a cat on my porch. Or if you don't like no cat, you can say there is not a cat on my porch. That's probably even better, right? Okay, so if I were to say, if I were to translate this statement into plain English, I would say it is not the case that, right? It is not the case that there is a cat on my porch and it is raining. Okay, so that must mean if P and Q, right, if P and Q is false, right, so in other words, we're saying that not P and Q is true, right, these statements really just make sense if you think about them just by assigning a value, in this case true. So I'm saying that this is true. Well, what would make it true? Well, it would have to be true just in case it is not the case that there is a cat on my porch and it is raining. What does that mean? Well, it means either there's not a cat on my porch or it is raining. Sorry, or it is not raining. If at least one of those makes it false, the whole thing is false, right? But that's exactly this right here, right? So it is not the case that there's a cat on my porch, or it is not raining. So that's the basic reasoning. And now we're going to do a table for each of them, and that will show that they are in fact equivalent. So I have P, Q, and I want to show that not P and Q and not P or not Q. I want to show that these are equal. Okay, so to show that they're equal, logically equivalent, we need to show that the final column of both of those tables would be the same. But rather than making two separate tables, because there would be a lot of redundancy, right, we'll just make them in the same table, save some space. Okay, so just based on what we see here, it's clear that I'm going to need not P, not Q, and P and Q. So I'm going to go ahead and do that right now. So this will be not P, not Q, and P and Q. Okay, and again, because there's two atomic variables, P and Q, there's going to be 2 to the 2 number of rows. In other words, 4 rows. Okay, so let's fill this in. So P can be true, Q can be true, P could be true, and Q false. P could be false with Q true, or they could both be false. Now, if P is true, then not P is false. This will be false. This will be true, true. This is going to be false, true, false, and true. Okay, so P and Q is true just in case both of these are true. So that would be the first one. And for the rest of them, at least one of them is false. So these are all false. This column is just going to take these results and it's going to negate them. So true is going to become false, and false is going to become true. Finally, this final column is true only when at least one of these values is true. So here they're both false, so this is false. Here, this is true, so the whole thing is true. Not P is true, so the whole thing is true. And both of them are true, so at least one is true, so the whole thing is true. And as we can see, because these last two are, because they have the same truth value distributions, false, true, 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 it has to be that they're logically equivalent. In other words, not P and Q is logically equivalent to not P or not Q. Okay, so next we're going to go through and I'm just going to mention the algebras, okay, the algebraic rules. Okay, so here they are. I'm going to go through them all really quick. So the first ones are the idempotent laws, okay? This says that P or P is equivalent to P. and P and P, that's equivalent to P. So this is the idempotent. And it shouldn't have an accent. That was just a little typo. Okay. The next one is associativity. So this is associativity. Okay, well, let's think about why this first one is true. Well, I already showed you basically why this one's true. This one's essentially the same thing, right? So if P is true, then this whole statement is true, right? And if P is false, this other P also has to be false. And because both P's are false, P or P is false. So P or P is false just exactly when P is false. So you can also conclude that P or P is logically equivalent to P and P. And I seem to be having some issue right now with my mouse. Oh, wow. Oh, there we go. Okay, good. So there we go. That's what I want. Okay, so the next is associativity. So let's go through that. This is P or Q or R. This is logically equivalent to P or Q or R. And also, you have another result that says if you replace the ors with ands, you still get the same result. Right? So often the way associativity is summarized is basically you can drop the parentheses. That's one way of thinking about it. Okay, so the next one is commutativity. And this just says that P or Q, this is the same thing as Q or P, right? Either Tim is taller than Jake, or 2 plus 2 is 7 is equivalent to 2 plus 2 is equal to 7, or Tim is taller than Jake. In other words, the word or is symmetric. Same thing with and. So P and Q, that's the same thing as Q and P. After that, we have distribution. So distribution is basically where, with associativity, the symbols were either all ands or all ors. And distribution is where at least one of them is different. So let's see, P or Q and R is equivalent to P or Q and P and R. Now, how can you think of this? It's kind of like if you had 2 times 3 plus 7, right? This is the same thing as 2 times 3 plus 2 times 7, right? So the operation on the outside, in this case multiplication, sort of gets pushed to the inside, right? So I can add little parentheses, and what I mean by inside, outside, is this is outside the parentheses, now it's inside the parentheses. Here, the or was outside the parentheses, now it's inside the parentheses, right? And here, addition was on the inside, and then it gets pushed outside. So this one right here, it's just like really, we've seen that for a very long time. It got, really drilled into us from an early age. This one, not so much, right? But really, it's the same thing, okay? The other form of distribution is where instead of down and up, you have up and down, right? And so these are all just going to flip. Yeah, like that. Okay, so if that doesn't make sense, just think, okay, if I had this right here, right, how would that work? Well, not actually the same way. Well, let's think about it. This would be 21 plus 2, that's 23, and this would be 6 times 2 times, 2 plus 7, and that'd be 5 times 14. These are definitely not equal, but the point is that in the case of logical operations, you could do that, right? So hopefully that makes sense. So in the case of addition and multiplication, we only have distribution like this. We don't have it like this, right? We can't swap them. But for logic symbols and an or, you can, okay? The last few are rather straightforward. It says that if you have p or true, right? The book just uses t, but they mean true. Then this is just going to be p. In other words, true doesn't. If you add a true statement to another statement, true doesn't affect it, right? And if you I'm sorry, I misspoke. If you add it like this, the whole thing is true, right? Because it's an or. But if you had and, right? If you have and, then this is just going to equal p, right? So the whole value of this, because true doesn't change anything, it's just going to go back to whatever p was. And likewise, if I have p or false, right? This is just going to depend on p. And if I have p and false, I should say false, then this is false, right? The whole thing depends on false. Finally, a few other rules, right? If you have not p, this is p. We already went over that. It's called double negation. And your English teacher would have called that a double negative. So if you wanted to give an example, to think of a simple example from language, you might say something like, it is not the case that I did not study, right? So that's just a really weird way of saying I studied, right? What are the other examples? Well, Some of these I already said, maybe I didn't write them down. If you're not true, then you're false. And if you're not false, you're true. And the law of excluded middle, right? It says that if you take any proposition and its negation, or rather, or its negation, right? That whole thing is true. And P and not P, this is false, okay? So this one is called the law of non-contradiction, sometimes also the law of contradiction. Okay, so that's all good. The final set of rules, kind of really the most important ones, are De Morgan's laws. De Morgan's laws. And I'm going to assign the proof that these laws hold as part of your homework. So these basically say that if you have this sort of statement, not P or Q, you can just push that negation through. So not P and not Q. And likewise, if you have not P and Q, this is the same thing as saying not P or not Q. Okay, so that's the algebra of propositions. I just gave you all the rules. So basically that tells you how to manipulate your symbols. With enough practice, it should be very, very easy to solve lots of these problems. See you in the next video.